Life likely began in a tangled web of chemical reactions, dozens, hundreds, perhaps thousands of molecules bumping into each other under early Earth's churning conditions. This isn't a neat three-step recipe in a textbook, but a messy reaction network where amino acids, nucleotides, lipids, and countless other compounds form, break apart, and reassemble in endless combinations. What makes prebiotic chemistry so chaotic? In lab simulations like the classic Miller-Urey experiment, you spark a mixture of simple gases and quickly end up with dozens of amino acids. And a lot of junk you didn't plan for. Early Earth would have presented UV light, volcanic gases, drying puddles, hydrothermal vents, and meteor rain all feeding into reaction pathways that crosstalk, compete, and create side products. Rather than a straight arrow from A to B, you get a spaghetti junction of reactions where useful building blocks are buried in noise. You never tease out the right pathways. Researchers ask whether life's core reactions, like forming RNA or fatty acid vesicles, can be isolated and reinforced within this chaos. By tweaking conditions, pH, temperature cycles, mineral surfaces, scientists have coaxed nucleotides to link into short RNA strands or fatty acids to self-assemble into primitive membranes. Yet every advance highlights new mess. Side reactions that chew up precious precursors, or mixed vesicles that collapse at the slightest disturbance. Is it hopelessly messy or modular? A growing view holds that life emerged not from one grand reaction, but from pockets of simpler, semi-isolated networks, protocells that concentrate specific chemistries. Imagine tiny droplets in rock fissures, each hosting a subset of reactions. Within these microenvironments, useful loops, say sugar phosphorylation or peptide formation, could dominate, while other droplets hosted different cycles. Over time, the winners merged, giving rise to more integrated systems. What examples point the way forward? In systems chemistry labs, teams mix nucleobases, sugars, and phosphates under drying wetting cycles that mimic tidal pools, generating short nucleic acid oligomers. Others flow amino acid mixtures through metal oxide surfaces that selectively bind and catalyze peptide bonds. Each success addresses a slice of the puzzle, but stitching these slices into a full lifelike network remains a grand challenge. So, are life's origins too messy to recreate? It's certainly daunting, but mess doesn't imply impossibility. By embracing network complexity rather than fighting it, researchers develop techniques to guide reaction flows, using microfluidic channels to simulate primordial rivulets, employing light-triggered catalysts to time reactions, or leveraging synthetic biology to reverse engineer minimal self-replicating systems. The goal isn't to rewind Earth's history exactly, but to uncover the general principles that let complexity organize into living systems. An origin of life chemistry may forever be less like baking a cake and more like tuning an orchestra of reaction pathways, each instrument playing its part in a densely interwoven symphony. We may never perfectly replay the first notes of life's concerto, but by understanding how messy networks can self-organize, we edge ever closer to hearing that cosmic overture for ourselves. Prebiotic reaction networks refer to the sets of chemical reactions that occurred on early Earth before life began, leading to the formation of biomolecules like amino acids, sugars, nucleotides, and lipids. These reactions were likely driven by energy sources such as ultraviolet light, lightning, hydrothermal heat, or mineral surfaces. Unlike tightly regulated metabolic pathways in cells today, these early networks were uncontrolled, heterogeneous, and highly context-dependent. They occurred in environments ranging from volcanic ponds to deep sea vents and atmospheric aerosols. Understanding these networks is essential for piecing together how non-living chemistry transitioned into living systems. The Miller-Urey experiment in 1953 produced amino acids by simulating early Earth conditions with lightning discharges in a gas mixture. It's like trying to assemble a computer by tossing parts into a storm and hoping they arrange themselves correctly. One major obstacle in prebiotic chemistry is the overwhelming number of possible side reactions that can occur alongside desired pathways. Without enzymes to channel specific reactions, chemical noise quickly overwhelms productive processes. This makes it difficult to obtain high yields of biologically relevant molecules. Even when key building blocks form, they are unstable or consumed by competing reactions. Thus, the origin of life may have depended on rare, self-sorting chemistries emerging from a noisy background. Attempts to synthesize RNA bases often result in dozens of undesirable byproducts, alongside trace amounts of usable nucleobases. It's like trying to bake a perfect cake in a kitchen where every ingredient keeps reacting with everything else at once. The early Earth had access to a vast number of organic compounds in physical environments, leading to combinatorial explosion, exponentially increasing numbers of possible reactions and intermediates. This explosion makes identifying plausible pathways daunting and reproducibility nearly impossible. For every useful molecule formed, hundreds of variants and non-functional analogs may also have appeared. This complexity makes it difficult to determine which pathways were realistic and which are lab artifacts. Reconstructing the exact chemical route to life becomes like tracing a specific river path in a web of flooded deltas. Prebiotic synthesis of sugars produces a tarry mixture with hundreds of sugar isomers, many of which have no biological function. It's like trying to find a working combination lock code by testing every possible 10-digit number blindfolded. Prebiotic reactions did not occur in controlled lab environments. They happened under variable temperatures, pH levels, radiation exposures, and concentrations. This environmental heterogeneity could have helped or hindered different stages of molecular evolution. Some regions might have favored polymerization, others favored energy harvesting or molecular stability. But reproducing these microenvironments in the lab is incredibly difficult. The messiness of early Earth may be essential for origin of life processes, but resists simplification. Laboratory simulations of hydrothermal vents show that steep temperature and mineral gradients can selectively stabilize certain molecules while degrading others. It's like trying to replay a jazz solo when the room, instrument, and air pressure keep changing mid-note. One proposed solution is that some reaction networks became autocatalytic, where the products of reactions accelerate their own formation, creating self-sustaining chemical loops. This network-level selection could filter the chaotic chemistry into more organized and functional patterns. Autocatalytic sets may have laid the groundwork for metabolism, enabling complexity to grow despite environmental messiness. These networks don't require full enzymes, just partial chemical reinforcement. However, identifying and replicating such networks in the lab remains a major challenge. The foremost reaction forms sugars and includes feedback loops where products catalyze earlier steps, albeit inefficiently. It's like a campfire that, once started, throws sparks to ignite nearby kindling, feeding itself without needing a match again. Even if chaotic reactions produced a soup of molecules, natural environments may have acted as filters. Wet-dry cycles, mineral surfaces, ice layers, and lipid membranes could selectively concentrate, stabilize, or catalyze useful molecules. This environmental selection might have helped prune the messy network, favoring a path toward biochemistry. Recreating such filters is key to making sense of the complexity. Life may have emerged not in spite of messiness, but because the mess created opportunities for selection. Clay minerals can catalyze RNA polymerization, favoring longer chains over random fragments. It's like a rocky stream bed where only the flattest, strongest pebbles make it through the rapids intact. Modern researchers try to build minimal models of prebiotic systems, including protocells, primitive RNA replicators, and chemical reaction cycles. While some components, e.g., lipid vesicles or short RNA strands, have been recreated, no complete self-replicating prebiotic system has yet been achieved. Most models work under narrow conditions or rely on lab-based interventions. This suggests that we still lack the right framework to integrate all parts into a single working origin scenario. Current reconstructions are fragments of a larger, unassembled puzzle. Researchers have built RNA molecules that can catalyze their own replication in ideal conditions, but not in messy, real-world environments. It's like having all the Lego pieces to build a spaceship, but no instructions, and the pieces keep sticking to each other randomly. Some theories suggest that complexity and noise were not obstacles, but essential ingredients in life's emergence. Rich chemical mixtures may have allowed for redundancy, exploration, and innovation, creating a reservoir of molecular diversity for selection to act upon. Messiness, in this view, was the engine of evolution long before biology began. The origin of life might not have been a clean path, but a chaotic search through chemical possibilities. Embracing this may change how we design experiments. Complex coastrovant droplets can spontaneously form and trap RNA, providing a possible model for early cell-like compartments. It's like evolution throwing paint at a canvas until a meaningful picture gradually emerges. The prebiotic reaction network is vast, tangled, and only partially understood, but it is not beyond exploration. While full recreation may be impossible, targeted reconstruction of plausible subsystems offers insight into how life might have begun. Accepting complexity as a necessary condition rather than a problem may guide better experimental design. Rather than a single path, life may have emerged from multiple interacting pathways filtered by time and environment. The origin of life may remain messy, but that mess may be the signature of nature's creativity. Ongoing research at the interface of systems chemistry, synthetic biology, and geochemistry continues to reveal new pieces of the origin puzzle. It's like trying to replay the first symphony ever composed without knowing the notes, but recognizing the melody in the echoes.